Alrighty, 143. So we talked about basic vector stuff the other day, last week, and so today we're going to talk about some vector operations. The first thing that we can do with a vector is multiply by a scalar. Okay, so a scalar says a vector can be multiplied by a real number k called a scalar. This will change the magnitude of the vector. So the length or the size, the distance. If k is negative, then the vector will reverse to the opposite direction. So if you remember when we talked about opposite vectors, if u and v are opposite, then u is equal to negative v, basically because it just reverses the operation. So the figure at the right shows various scalars of vector v. So here's vector v. Here's 2 times vector v, which it has the same angle, so we're going in the same direction. It's just twice as long. 1/2 v, same direction, but half as long. And then negative v, same length, but opposite direction. Okay, easy enough? You're literally just going to multiply. All right, so then we can add vectors. So adding vectors, here's a geometric representation, just means a visual representation of the addition of 2 vectors v and w are shown at the right. The vectors are positioned so that the tip of v coincides with the tail of w. So this is the tail of v, the tip of v. So wherever v ends, then w starts, right? And their angles have to stay like however they are. And then you just literally add them together. It's like finishing a triangle. Okay? So the sum of the vectors is called the resultant. And it extends from the tail of v to the tip of w. So it's called the resultant vector. We can also subtract vectors, which would be the difference of 2 vectors. We can say it's v minus w or v plus negative w, same thing. So here's the geometric representation using the same tip to tail. So here's v, and then here's negative w. And then when you do that, there is your resultant of v minus w. Easy enough? We're going to look at more of it from an algebraic standpoint than a geometric standpoint, really. But that's what's happening with your vectors once we start applying it. All right, so we have some rules here. We have vector v is a1, b1, w is a2, b2, and vectors are vectors, and k is a real number. So if that happens, then your scalar multiplication just looks like this. It's k, oh, I'm totally writing the wrong thing. K times a1, and then k times b1. That's what it looks like. You're just multiplying it across. So then when I want to add them, looks like this. A1 plus A2, comma, B1 plus B2. Just like when you would add ordered pairs that were coordinate points. Subtraction, A1 minus A2, B1 minus B2. It all really is that easy. What questions do you have? All right, let's jump to number 3 here. So we have these vectors that are defined for us. We have A, B, and C that are defined for us. We want to do C minus B. That means it's going to be negative 4 minus 1 and 5 minus 7. So vector C minus vector B is going to be negative 5, negative, oh, goodness, sorry, I leaned on that. Negative 2. Everybody okay with that? All right, so let's do number 4. We have A minus 3C. So A is negative 6 minus 3 times a negative 4. Then 2 minus 3 times a positive 5. So vector A minus 3 times vector C. This is going to give me negative 6 plus 12, which will give me a positive 6. And then that's a negative 15 and a positive 2, negative 13. What questions do you have? All right, again, no tricks. It really is that easy. All right, so flip it over on the back. You're going to do number 5. I'll write A and B up here again, though, so you don't have to flip back and forth. A is at negative 6, 2. B is 1, 7. So just do number 5. So, did you get this? Check to make sure we agree. -4, -6. Yes? Awesome. All right, so let's talk about unit vectors, okay? Because we're about to get this onto the unit circle. So just like we could have any circle, any radius, we can find sine and cosine and do all those sorts of things, but everything all gets reduced down to the unit circle. We can also reduce our vectors down to unit vectors, okay? So with our unit vector, looks like this, U for unit vector, has a magnitude of, a vector with a magnitude of 1 is called a unit vector. All right, so if it is so this right here, the magnitude of U is 1 because that is a unit vector. Right? It's like the most reduced form of that. So it says, given any non-zero vector V, a unit vector U in the same direction of V can be written using the following rule. The unit vector is equal to 1 over the magnitude of vector V times vector V. Or the vector divided by the magnitude, either way. Remember that little double absolute value thing is not absolute value, it is the magnitude. So if I take 1 over the magnitude times the vector, that will give me the unit form of that vector. Okay, we'll talk more about why we care and what we're going to do with them, but we've got to get it first. So we are going to use that to find a unit vector U with the same direction as the given vector. We will do number 7 first. So what I need for this, I need to find the magnitude. How do I find the magnitude? What do we do to find the magnitude? Square root of a squared plus b squared, right? So it's just a little Pythagorean theorem. So it's just the square root of -5 squared plus 12 squared. So square root of 25 plus 144, square root of 169. So the magnitude of V is 13. That's a Pythagorean triple. It's a 5, 12, 13. You wouldn't have to do all that, but even though, like, if you don't know them, that was pretty easy to get through, so it's no big deal. So I have the magnitude. So now I want to find the unit vector. It is equal to 1 over that magnitude times the vector itself, which is -5, 12. Which means my unit form of the vector is -5 thirteenths, 12 thirteenths. So that is a vector that has the same direction as V, but is only 1 unit long. What questions do you have? All right. Let's do 10 together, and then I'll have you do 1. So I need to find the magnitude of K. That's going to be equal to the square root of 16 squared plus -8 squared. What's 16 squared? 256 plus 64. So that gives me the square root of 320. And I know I told you to get your calculator, but that's not what this is for. This should be something you should be able to do without it. So let's talk about simplifying these the easy way. Not everything has to have a full tree or a full birthday cake or whatever it is you want to call it. Yes, finding the largest perfect square that divides into there makes it easier, but then sometimes you have to guess and check on that. If I'm going to have the square root of 320, well, that ends in 0. So 32 and 10, pretty easy, right? Well, I know a perfect square that divides into that. That'd be 16. There's my perfect square. Here's my prime number. And then 10 is 2 and 5, right? So I can take the square root of my perfect square. I can take these pairs out as a 2. That stays underneath. And that's where I'm going to get the 8 square root of 5. Something you got to be able to do very quickly and accurately without a calculator. All right. Always good if you have one with you, check yourself, but you got to practice without it as well. All right, so that means that the unit vector is equal to 1 over 8 square root of 5 times 16 -8. So yes, I'm going to have to rationalize, but I don't want to do it at this point because it'll be way easier if I wait. If I do this, I'm going to get 2 over the square root of 5 and then negative 1 over the square root of 5. So now if I rationalize, you get 2 square root of 5 over 5 and negative square root of 5 over 5. What questions do you have? All right, good deal. So let's look at 12. Well, before I can find the magnitude, what do I need to do? Well, before I find the magnitude, I got to find the vector. So I need the component form of the vector, right? So vector PQ, how do I find the component form? x2 minus x1, right? 8 minus a negative 1 is 9. Negative 2 minus 4 is negative 6. Then I can find the magnitude. Magnitude of PQ is equal to the square root of 9 squared plus negative 6 squared. So that's going to be the square root of 117. Let's talk about 117. If I add the 1, and the 7, what do I get? 9, which means that's divisible by what? 3 and 9. Okay, that works for 9 also. So if anything's divisible by 9, it's divisible by 3, right? And 9 and 3 are the only ones this works for. But so if I add that up, since 1, 1, and 7 gives me 9, then square root of 117 is divisible by 9. That's a perfect square, so that's helpful right here, right? So 117 divisible by 9, well, 9 goes into 11 once with 2 left over, and that would be 3. That's a prime number. That's a perfect square. So this gives me 3 square root of 13. Instead of staring at it and wondering if it is prime or not, or assuming that it is because it looks like a weird number. All right, you go ahead and finish this one up. All right, see if we agree. What questions do you have? Good? Easy enough? Alrighty, then let's move on to the next piece of paper if there are no questions. This is going on 144. So we've talked about vectors, we've talked about unit vectors, so now we're going to talk about standard unit vectors and another way to write vectors out. Our standard unit vectors, I and j, are positioned along the x and y axis. So here is vector I, here is vector j. Okay, so these points here, this point is 1, 0, this point is 0, 1. So the vector itself, to give me distance and direction, right, is going to be for I, the vector itself is also 1, 0, and j is 0, 1. But those, whether you got the parentheses or the pointy brackets, they mean completely different things. Okay. So we can have a vector in this form, which remember that is called the component form. I can have a vector that's in component form, but it can also be written in the form A times I plus B times J, and that is called a linear combination of vectors, I and J. The A part just goes with the I, and the second part goes with the J. It says, follow the steps below to prove that these things are equal. Okay, so we're going to prove that they are equal. We're given this vector AB. We're going to start by rewriting it as the sum of two vectors. So vector V could be written as A0 plus 0B. Do you agree with that? If I took these and I added them together and I went backwards, would I end up with the vector AB? I would, right? So then the second step is to factor out A and B. So vector V can be equal to A times 1, 0 plus B times 0, 1. And again, at every step, I should be able to go backwards and end up where I was. So if I take this A and I distribute it in there, I'd end up with this. Take the B and distribute it, I'd end up with this. So now since we have defined I and J as these two vectors here, when I substitute them, vector V is just A times I plus B times J. There's a little proof. Okay? What questions do you have? All right. So now we're going to rewrite each vector as a linear combination of I and J. So this means that this vector here is just going to be 2 times I plus 5 times J. See how easy that is? It's just a different way to write the vector itself. So number 2, oh, that's not B anymore. It is N. So this is going to be negative 7I plus 3J. Number 3, what do I have to get before I can do that? What form, what is it called? Component form. I need the component form of the vector. So vector RS is going to be equal to, remember that's negative 5 minus a negative 9 and negative 6 minus 8. So it's going to give me 4, negative 14. Which means that vector RS can also be written as 4I minus 14J. All right. What questions do you have? Component form versus linear combination. So let's talk about trig forms. Talk about the trig form of a unit vector first. Okay, so the unit vector is like what we just talked about. It says if U is a unit vector, so here's my U, it is a unit vector. This is the terminal point, right? Where the tip is, right there. It says then the terminal point U lies on the unit circle. Because again, all of this is very much intertwined. Okay, it lies on the unit circle. On the unit circle, these ordered pairs that we had that is labeled as AB right here, we had them labeled as XY sometimes. What did the ordered pair represent on our unit circle? The cosine or sine of the angle, right? The X value was the cosine of theta, the Y value is the sine of theta, yes? Okay, and it's truly just cosine theta and sine theta when it is the unit circle, and that's where some of y'all got things mixed up. If the radius isn't 1, then it is r cosine theta and r sine theta, but if the radius is 1, the r is irrelevant. So again, this radius is 1. So your unit vector on the unit circle here, AB, can be written as unit vector is equal to cosine theta, sine theta. It's the same thing. If I'm going to write it as a linear combination, then U is equal to cosine theta I plus sine theta J. What questions do you have? Same type of stuff, because again, it's all related to each other. So that's for a unit vector. If it is not a unit vector and the magnitude is not 1, that's any other vector. Right? So let's look at what happens with those for any other vector. It says because every vector V is a product, it's a product of its magnitude and its corresponding unit vector, we can write this in the following forms. Now I want you to remember that your unit vector that we had is equal to 1 over the magnitude of V times the vector itself, right? That's what we did on that other page. So if I want to solve for V, All I'm doing is multiplying both sides by the magnitude. That's where this comes from right there. Does that make sense to you? So since that is true, and we're talking trig stuff here, then the magnitude of v times that unit vector right here, cosine theta, sine theta, because that magnitude is like the length of the radius, right? Which then we can distribute that in, and we get the magnitude of v times cosine theta, magnitude of v times sine theta. Then our linear combination is magnitude of v times cosine theta I plus magnitude of v times the sine theta j. R cosine theta, R sine theta. It's all the same thing. You're just applying it to different types of applications. Okay. It could be written as I cosine theta. That is a very good question. You do not multiply I times theta before you take the cosine. So yeah, it's like we should have a little times there. Very good question. All right, so oh shoot, I forgot to erase that part. Let me rewrite that. No, I just erased it to rewrite it all, but whatever. So v is equal to the magnitude of the vector times cosine theta. This is what we just wrote on the front. I'm just rewriting it back here. Magnitude of v times sine theta. So this says, find the component form. Now remember, component form means the vector that looks like this. Find the component form of each vector with the given magnitude and direction angle. So we're going to start with number 5. If I want the component form, it's got to look like this. I'm given the magnitude and I'm given theta. So that means that vector v is equal to 8 times the cosine of 60 and then 8 times the sine of 60. What is 60 in radians? Pi thirds, right? So what's the cosine of pi thirds? 1/2. So this is 8 times 1/2, and then 8 times what? Square root of 3 over 2. That means your vector v is equal to 4 square root of 3. Okay. What questions do you have? All right, on number 8, I want you to do this first step for number 8. All right, so you agree with that much? Now, is 340 a special angle? It's 20 away from 360. So do we have 20s in our special? So it's not. So since it's not a special angle, that's why you have your calculator. We need to make sure the calculator is what? Degree mode. If it is not, put it in degree mode, and then you just type this in and sit. If you didn't get it at the beginning, you don't. Oh, Isaac, sit. If you didn't get it at the beginning, you don't get it now. And whatever the signs end up being, then that is what it is. You should get, what is it, 28.191 and negative 10.261. Make sure you agree with that. Okay. What questions do you have? All right, good deal. So that's taking the trig information and putting it into component form. And now we're going to go the opposite direction. And it says, write each vector in trigonometric form, okay, which means in the end, there's going to be trig left in it. Okay, so that's how you need to make sure, you got to know when to stop when you're doing these. So let's start with number 10. In order for me to put it in trig form, I need the magnitude and I need the angle. I have the component form of the vector, right? How do I find the magnitude? square root of, yeah. So the magnitude of m is the square root of negative 3 square root of 2 squared plus negative 6 square root of 6 squared. So what's negative 3 square root of 2 squared? It's going to be 18, right? So it's 18 plus 6, so it's the square root of 24, 2 square root of 6. That really should be way faster than you trying to type stuff in. I mean, just knowing how to get through that. So there's your magnitude. So then I need theta, right? And this is totally a non-calculator question. So then I need theta. And how do I find theta? Tangent inverse of y over x, so negative square root of 6 over negative 3 square root of 2. So when I simplify this right here, can I simplify those square roots? Like, can I make that just a square root of 3 on the top? No, you totally can't. Anything inside the square root you can deal with, anything outside the square root. So this just becomes the tangent inverse of square root of 3 over 3. What's the tangent inverse of the square root of 3 over 3? Pi 6, right? But we have to pay attention to what's going on. You have to pay attention to your quadrants when you get these angles, right? So what quadrant is this directed towards? Third. This is the third quadrant. This is what I ended up with. I need my third quadrant pi 6 angle, but really I need it in degrees. So it's probably easier to go ahead. What is pi 6 in degrees? 30, right? So I need my third quadrant 30-degree angle. What's that going to be? 210. Okay. So 210 degrees is the angle that I'm actually using. Everybody with me so far? So my vector m then is 2 square root of 6 times the cosine of 210, and then 2 square root of 6 times the sine of 210. And that is my answer. Don't evaluate that, because if you evaluate that, you're going to end up right back here and you're going to be going in circles, right? If you were told to put it in trig form, it has trig in it. It clearly has trig in it. Does that make sense to you? Otherwise, you're just going to be going in circles and then you're going to be confused. Okay. What questions do you have? All right, let's look at number 12. Number 12 is in the linear combination form. In order for me to be able to do what I need to do and for it to make sense to me, then I really need it in component form. So what is this vector in component form? Negative 2, 2. It's that easy, right? Just take away from I, take away from j. All right, so go ahead and work on that. Find the magnitude. This should all be done without a calculator. Find the magnitude. Find the angle. Do you agree with what I have so far? I got 2 square root of 2 for the magnitude, and then the tangent inverse of negative 1 is negative pi fourths, which means that's negative 45 degrees, right? But what quadrant am I directed towards? The second quadrant. So I need my second quadrant, 45-degree angle. What's that going to be? Yes, and yes, it is. And then as in degrees, 135. In whichever way is it easier for you to think of, get the radians and then the degrees or whatever. So it's 135. That means we get 2 square root of 2 times the cosine of 135 and then 2 square root of 2 times the sine of 135. All right. What questions do you have? All right. So 14 ends up a little bit different, so I'll walk through this one with you too. All right, but I have these 2 points. In order for me to begin this, I need this in component form. So my vector yz is going to be 5 minus 3, which is 2. Negative 8 minus a negative 2 is going to be negative 6. So then the magnitude of yz is going to be equal to the square root of 2 squared plus negative 6 squared, square root of 40, which is 2 square root of 10. There's my magnitude. Then I have to find theta. So theta is equal to the tangent inverse of negative 6 over 2. That's going to give me a negative 3. So when it gives me that negative 3, is negative 3 a special value? No. And again, that's why you have your calculator. So you take the inverse, and it gives you negative 71 something, right? Make sure that I'm right about that. I'm not making it up. Is it negative 71 something? Okay. And then, but that is this angle that they gave me is in which quadrant? This negative 71 degrees. It's in the 4th quadrant. This is directed towards what? The 4th quadrant. I do want a 4th quadrant angle. However, I don't want it to be negative. So what do I do to get the angle I want? Add 360 to it. So what you end up getting for your angle is 288.435, which means your answer in the end for the vector is 2 square root of 10 times the cosine of 288.435 and 2 square root of 10 times the sine of 288.435 degrees. Remember, if you want it in trig form, it has trig in the answer. What questions do you have? We good? Awesome. All right, so go ahead and get that glued or taped in.